Welcome everyone. Earlier this year, we formed a new community called Dynamic Abstractions, bringing together professionals and researchers to discuss and demonstrate how dynamic representations on new notations or new abstractions can facilitate powerful ways of thinking and problem solving. One specific point of interest in our group is how dynamic abstraction would enable creators to create their own tools. Today, with some of my colleagues and community members, I'm really excited to share and discuss our ideas. And we would like to discuss our idea by grounding around an example called Feynman Diagram. First introduced in 1948, Feynman Diagram was first proposed by Dr. Richard Feynman. It is a pictorial representation in theoretical physics that demonstrates how subatomic particles interact with each other. So before this tool, theoretical physicists often use mathematics to do the calculation and computation, which was very difficult to maintain and obviously difficult to understand. But since the invention of Feynman diagram, theoretical physics became much more easier to understand and accessible. It was widely adopted in many other domains. And it was not just a powerful pedagogical tool, it was also a very powerful tool for computation. As Frank Wilson mentioned, that his Nobel Award-winning computations were unthinkable without Feynman diagram. So the reason we are grounding our conversation around this tool is because, first of all, it exemplifies the invention of a powerful tool and the impact it can have in a certain domain. We also know some of the characteristics that made it so powerful and widely adopted. There were also a number of challenges in the early days of its adoption. So as we are looking into the future of tool building, we can also reflect to the past and learn from the history of this tool and from some of its limitations. Alright, so in this design fiction talk, we ask, what if there existed a parallel universe where Richard Feynman would recreate or reinvent these diagrams, but with powerful computational tools and an AI assistant? How would the process look like? How would this diagram look like? And to share and clarify our vision, we will share the story of Feynman's Stylus. Some disclaimers: we are not theoretical physicists, and our goal in this talk is not to propose any new Feynman diagram, but to explore and raise questions about human-computer interactions as creators build new tools. This Richard Feynman in the parallel universe has agreed to host us so that we can take a look of his process of inventing this new diagram. And to do that, we are going to take a spaceship, navigate through space and time, and get to his universe. And there he is, our Richard Feynman in the parallel universe. Super excited to meet him, and let us introduce ourselves. Hi Feynman, I'm Rubaiyat Habib, an HCI researcher interested in creativity tools and digital animation.
I am Nazmul Sakib, Dr. Feynman, and I'm interested in visual and embodied mathematics.
Hi, I'm Sang-Ho Seo. I'm a researcher interested in augmenting human intelligence and creativity.
Hi, I'm Ian Arajo. I am an assistant professor at the University of Montreal. And hey, Feynman, I'm interested in dynamic notation.
Now, as Feynman is taking us to his workspace, he's also giving us some context in this universe. Theoretical physics is also in an inflection point, but most of the physicists are still using mathematics. But Feynman's intuition is that there might be a better tool that will simplify the process. All right, before diving into the parallel universe Feynman's workflow, let's take a step back here. Let's think about what happened in our universe almost 75 years ago, right? This is Richard Feynman in our universe and drawing the first Feynman diagram in pen and paper. So what happened is that, for those who are not familiar with it, there are two particles, photons, that are coming close to each other, and one of them is emitting an energy and the other one is absorbing the energy. Now it is kind of a dynamic phenomenon, right? But because it was pen and paper, Feynman had to use like an axis, like a pictorial representations like the one we see, t dimensions on the vertical axis and s on the horizontal axis. Anything you want to add, Sangho?
Yeah, I think it's just as you mentioned in the beginning, I think it's just quite fascinating that before he introduced this diagram, like as this very simple diagram, all the physicists primarily relied on these long complex equations to describe and make sense of how particles interacted, and by just taking on this visual approach, which was quite unconventional at the time, that he transformed how people think about it. And I think it's kind of interesting. I think we can overlook how these simple representations can influence the way we think. But I think I love how this story of the Feynman diagram changing how people think in significant ways. I think it's a really kind of a fabulous story, and I'm excited to talk about this with you all.
Yeah, exactly. So now coming back to the present tense, like in this parallel universe, Feynman has a wildly different setup. He's starting his work in a computational medium with, a digital whiteboard and a stylus and a powerful AI assistant, which we are calling Maya. So I'm actually quite curious to see how these diagrams turn out and how would they differ at the end of the session, how would it look like and how it compare like the one we have in our universe. All right.
Okay, so it seems like Dr. Feynman is first tried to simplify it by creating an abstraction of this complex behavior. I wonder if the way he develops this simpler model is different from how we do it. So let's see. Okay, so I see that he's asking his AI assistant to remove excess particles so that it can focus on the simple interactions between a few particles. Okay, that makes sense. And now, all right, so he has this animation, and now we see that he's building, I think, initial abstractions by observing the animated behaviors of the particles and energy, and then turning them into simple diagrams like the Feynman diagrams that we are familiar with. And I think what's interesting here is that basically these diagrams convey the same information as in the static diagrams that we have, but in this digital medium we see that they're animated, which I guess is helping to leverage our intuitive sense of space and time.
Yeah, it's kind of interesting and always fascinating to see how people invent new notations and diagrams.
Yeah, I agree, and that is why I also love reading the literature in cognitive science, because they discuss precisely how through what mechanisms these representations like also enable us to think what we previously couldn't think of as the new representations have been developed throughout the course of the history. So for example, right, we use these diagrams and notations to express abstract complex concepts and procedures. And what happens is that by stripping away these irrelevant details and turning core ideas into these objects of thoughts, which are expressed in, say, notations and diagrams, representations help us make sense of these complex realities. And it looks like this is what Dr. Feynman is also doing here, which is great to see. But he's also doing something cool by animating these diagrams. And as an HSL researcher, when I look at these cool interactions, I can't help but wonder, whether there are ways to help users easily create these animations. And I know, Rubaiyat, you have worked on these very cool projects for animating these drawings. So do you want to talk about that?
Yeah, I mean, his process of abstraction, the way he came up with the particles actually reminded me of this work, which we did a while back. We're trying to create tools for animators who could use it to create fires and smoke. And it's a challenging problem because typically, animators use physics-based simulation tools, which is hard to control and stylize and understand, classical computer graphics problem. And we were also like having trouble using the Navier-Stokes equation at the early stages, but I remember my colleague at the time pointed out that this very old SIGGRAPH paper that actually approximated animation aerodynamics using these very simple flow primitives. So that is a great example of abstraction, right? A complex physics simulation into these primitive atomic blocks, which actually you have taken inspiration from and designed energy particles. So instead of so our process of abstraction was, instead of using physics simulation, using these energy particles to create repeatable patterns, but the users can use them to create complexity in an interactive, iterative way. So this abstraction really help us to create something that is understandable and controllable, right? Users know exactly what is happening. Yeah.
Yeah, that's really cool. I love how you enabled users to create something complex by allowing them to leverage these composable elements. And I'm sure we'll see the parallel in the animation that Dr. Feynman looks at. As physics is also governed by a set of rules and principles. So I'd love to see what he's doing with that.
Yeah, I think one of the limitation of what we have right now is looks like they don't have any rules. They're simply animated. But if someone wants to interact with these particles, they need more than that. They need to be governed by a set of rules. All right, let's see what he does next.
So it seems like he's trying to create dynamic simulation, seemingly by writing down rules, maybe. I don't know. Something is happening, but I don't know what he's actually doing here.
Yeah, I mean, like, let's see where he lands. But I mean, as I'm looking at this process, it reminded me of Ken Perlin's seminal Chalk Talk. If you haven't seen that project or talk, you should take a look at it. I mean, he was arguing that in the future, interactive computer graphics will become part of our language, and we will be as fluent as using our language. And I think that kind of reminded me of his visionary talk here. And more lately, I mean, there was this work from led by Carl Rosenberg named Draw Talking that looked at how can we create a dynamic simulation using simple sketches and narrations. You sketch something and you say how your sketches will interact in this world simply by narrating, and that creates an interactive simulation. So I think this latest works in HCI in our universe using a variety of simulations, complex simulations without programming is really promising, and looks like Feynman probably doing something along that line. He's trying to create a simulated world, but without doing programming. All right, coming back to Feynman, it looks like we have an interactive simulation here. He used his powerful AI assistants. He did some sketching, and he wrote down some rules in the form of natural languages and other expressions. And now, as he is interacting with this particular different possibilities that can happen between these interactions. It's kind of fascinating. So it looks like it's quite different from what we had in our universe. At the end of this section, we have a Feynman diagram that is an interactive simulation. I wonder how Feynman would, validate this diagram to his peers who are working in theoretical physics.
Okay, so it seems like we have a visit from Dr. Dyson, who's a physicist and a colleague of Dr. Feynman, visiting his office, and he sees what Dr. Feynman is doing, and seems like he's suggesting that or reminding Dr. Feynman that physicists think in math and not in pictures. Okay, and Dr. Feynman seems to be asking his AI assistant to pull up the mapping that he has created based on the natural language specification. And it was like, okay, that seems to be the table that he created. And now it seems like Dr. Feynman is asking Dr. Dyson to check whether his math and mapping is correct. And And Dr. Dyson helps out by saying that it's correct. Okay. And Dr. Feynman is also asking the AI assistants to apply the color encoding for clarity.
Next.
All right, so I see that the AI assistant is now asking Dr. Feynman to confirm whether this mapping and is correct. And okay, so that animation is really cool, transforming from one representation to another. Yeah, I love this animation, like going from one representation to another, because in my research also, that has been, one of my main research interests. And it's also called like moving up and down the ladder abstraction. And the reason why I'm really fascinated by this is because representations, they engage different cognitive faculties in us, and sometimes for certain tasks, particular representation is more appropriate, as we saw. For more intuitive understanding, pictorial representations can be better compared to mathematical representations, which require you to think more in a more abstract sense. So, and oftentimes our human mind is dynamic, right? We need to think at a very abstract level, but sometimes think in a very concrete sense. So I think what really motivates my research is that having these dynamic representations that can align and with this evolving nature of human cognition. And I think that will be the key to really empowering our communication and learning. So I think that's really cool.
Next.
And so in one of my research, I worked on generating comics from code, and this was particularly in the domain of teaching programming, trying to make coding more accessible. And this kind of exemplifies what I was talking about, right? Sometimes when we're trying to make sense, sometimes these pictorial representations that are based on stories can be more accessible than kind of dry, abstract code. And one of the things that I found really interesting was that, which I didn't know before starting the research, was how challenging and difficult it can be to figure out how to map one representation to another, right? So let's say you have a piece of code. How should you illustrate that in the form of comics? If you think about it, there are multiple ways to express it. And there are many design kind of trade-offs and considerations to be made. So I'm not going to go into details, but one of the things I've found is that it's important to kind of explore the trade-offs, and sometimes, in my case, it was like doing this one-to-one mapping between representations that I found to be essential for making the corresponding relationships clear. And Sakib, I know you did something similar in math, which one of my favorite works. So if you want to take on and talk about that,
Yeah,
I'd love for people to find out about it.
Yeah, thank you, Sangho. So yes, definitely. I have done some work in visual and embodied mathematics where some of the same questions that you asked, Sangho, I think those are very relevant in my research too. Specifically, the part where you said math can be pictorial, right? And it doesn't have to be let's say symbolic, or it doesn't have to be a very abstract representation. I've been doing a lot of work on that front. But before I go into that territory, I wanted to take a little bit of time to talk about some fundamental cognitive science behind the work that I've been doing. I wanted to point out this work by George Lakoff and Rafael Nunez. It's a book called Where Mathematics Comes From. It's an amazing book, and these cognitive scientists show that we have some very fundamental cognitive capabilities that give rise to layers of representations, and eventually, and they call it metaphors. And eventually these layers of metaphors give rise to more complex mathematics. So for example, let's say fundamental cognitive ability like length of objects, we can discriminate between different lengths of objects, and they show that how that gave rise to the model of a number line, and how eventually that gave rise to real analysis in math, right? Yeah, so similarly, like we are able to discriminate objects, which means we are able to count a small finite set of objects. And from there, like based on grouping and counting, we invented set theory. So the important part for us to understand is the, building representations. We have been doing it forever in order to think, right? Sangho, like you already talked about this paper, like how we are able to think using external representation. And mathematics is nothing but creating external representations based on, like some of our fundamental cognitive abilities, creating layers of those representations, and that's how we build up mathematics. And that part is very important to me, because in this particular diagram, what you're seeing is uh, I tried to lay out what is the sequence of mathematics that we learn over our lifetime. So we really start with, tactile materials, like we draw stuff in our childhood. We are learning to count. We use actions and gestures to move and group different objects. That's how we start learning some of the addition and subtraction principles. And then there is picture-based math that we start learning in books. And a lot of these things are actually part of what I call embodied mathematics. However, there is a shift in our education and like the way we start doing math, where a lot of symbol manipulation starts coming up, and we don't know why we're doing the symbol manipulation. At least when we're learning, when we're starting to learn, algebra is not very natural and intuitive. So the abstractions keep increasing, and there is no natural way to move between these abstractions yet. Uh, so this particular work, what it tries to do is it takes the very first leap into what I showed in the last diagram, where there is a spectrum of picture-based math or embodied math to abstract mathematics. It takes the first leap into connecting those two and moving between these two worlds seamlessly. So, and then as I said, the algebra doesn't have to be only symbolic. Like you can do picture-based math, and what would that look like? And of course, like Feynman at this point would be thinking, how would you do that? Because like physicists and mathematicians and the experts are so used to thinking in symbols that like they probably can't imagine doing sophisticated mathematics using just pictures, or using embodied mathematics. So let's look at a very first simple example of how we could actually build up symbolic mathematics using picture-based mathematics. So in this example, what we're looking at is on the left, we have some expressions, like some algebraic expressions. So let's say the problem that we are trying to resolve over here is there are some students living in one house and some teachers living in another house. And we are trying to show the sum of students and teachers, or really the sum of number of elements in each of these houses, right? So that would be H1 plus H2. On the left, you have the set theoretic and the addition symbol that's representing the algebraic relationship over here. On the right, you have a pictorial representation that embodies the same information, essentially. And there must be a way to actually build up this picture so that we can move between these two worlds seamlessly. So over here, like I'm showing a demo of from the paper that I've just shown. I'm making some elements like very quickly. I can define lists, just like the way we understand sets, and like list is a form of ordered set. And I'm just building like a window or really a room representation and putting in elements over there. And each of these lists can count, and they can count at a hierarchical level. And what you are also seeing is that like I'm creating this street that actually contains both of these houses, right? But then each of these elements that we're drawing is a mathematical element. Over here, what you're seeing is there is a slider that we can move between these abstractions. This is a symbolic abstraction, and we can come back down in the abstraction layer to recreate the pictorial representation too. We show we are able to show a hybrid representation between symbolic and the pictorial math. With these three layers of abstraction, what we are seeing is we can move from the pictorial representation to the abstract representation and go back again to the pictorial representation on demand, right? So, and there is another example of work that I want to show in this context. This work was based on graph networks and how we can do something similar, but now we have images and videos from the real world, which are like picture based, and then from there we create graph network representation from these pictures, and then from there we can also go further up in abstractions. On the left of this cover image, you're seeing that like there are different graph abstractions that network scientists and graph theorists use, and we can move back and forth between these different layers. This might be a little interesting to Dr. Feynman because the next example I'm going to show is essentially fireflies example, and physicists always study fireflies, specifically physicists who are interested in chaos theory and nonlinear dynamics. So there are patterns in which fireflies synchronize their when they're blinking, and it's a very interesting problem to study in nonlinear dynamics. So if I take this video and kind of open up this notebook-like interface that we created, load this video, and then define some parameters for how to extract a graph network out of it. Then in every frame we're getting a different graph network, and this is what the result would look like. And then like we can actually take these graph networks, do some graph analysis on the notebook right away, move between these different layers, and also kind of see before synchronization and after synchronization how dense the patterns are, and then how the representations of these two different scenarios, like the synced network and pre-synced network, how are they different, and we can move back and forth between these abstraction layers in this particular work. So Feynman must be wondering at this point, like whether this can be extended to other fields. So like I have shown some work that I've done in algebra, and then I have shown some work that I've done in graphs, and then there is work that I'm currently doing in differential equations where we can actually create like this visual, go from visual representations to like symbolic representations. So in all of these, we are in a way we are moving between the iconic world to a symbolic world, and the movement has to be bidirectional, and that is a challenge. I just want to point out to Dr. Feynman that it is always a challenge, because when we're moving between these two representations and we make one change in the symbolic world, we want to come back to the iconic world. If we want to keep the mapping same, then we need it's really challenging, and like we really need to figure out some of the inverse problems over here. We need to solve for those inverse problems, and that's where AI can help us. Let's say tools like symbolic regression can be very useful in this context. I think the future of mathematics is interactive, and it is going to be a movement between symbolic and iconic worlds, and we do need to figure out how do we do bidirectional abstractions, and how do you move between these abstractions easily, and that's where AI can help.
Thank you, Sakib. Looks like at the end of this section, we have a Feynman diagram, which is simultaneously interactive, symbolic, and iconic. So I think the question I have in mind is, what's next? Will the broader community adopt this new tool? If yes, how?
So thank you, Rubiet, Sengho, and Sakib. So far, we've investigated how abstractions can be dynamic, how we can move through different abstractions, how abstractions could be interactive. However, most of our explorations have been largely focused on single individuals and single interactions with one user. In the real world, in how notations develop, they often develop among communities of people or through resistance when the notations meet the practical realities of everyday work. One book I really love is this book, Drawing Theories Apart by David Kaiser, which traces how Feynman diagrams in our world, in our reality, spread across the world. One thing I was really surprised about by this is that the reason we know about Feynman diagrams, you would think it would be about Feynman, but in fact, it seems like the chief reason is because of the substantial work that the physicist Feynman Dyson did in order to popularize the method. Other things in this work, we start to realize that when Feynman diagrams spread, Feynman didn't necessarily agree with all of their uses and all of their adaptations. And physicists adapted Feynman diagrams in new situations and had to maybe break some of the original rules that Feynman had set out. So if it wasn't for Dyson, we might not be talking about Feynman diagrams today. And indeed, today, Feynman diagrams continue to be used, but they've been adapted quite a bit. For instance, the squiggly line here between the U and the D are terms that Feynman himself would not have used. In fact, this entire diagram might make no sense to Feynman if we go back to our universe in the 1940s. So let's go to our alternate universe Feynman and ask that in his universe, why do they know about Feynman diagrams? So it turns out that Feynman was thinking here, looks like he's thinking, and he wonders how other physicists will take his dynamic abstraction. Okay. So he first prepares to share his dynamic abstraction with the rest of the world. And in this alternate universe, there is an intercommunication network like the internet, and he posts it for other people to find. And Feynman Dyson, who's his close friend and follower on these social networks, remixes and reshares his dynamic abstraction using a similar AI assistant. Now, Feynman Dyson prepares it a little bit better than Feynman did, and for some reason, it gets 100 million views in 24 hours, so it goes viral. And of course, other physicists take notice, and it spreads through the internet in this form. So physicists might, for instance, start to use it in their papers, or they might adapt the notation to their particular circumstance like they did in our world, using a similar AI assistant. But it's not just physicists who would be impacted in this alternate world, unlike our world. Next. You might imagine an educator in a high school classroom teaching physics who wants to convey the news of the current developments and uses an AI assistant to translate this dynamic abstraction, this dynamic representation, to explanations for their students. Or you might consider a person wearing a mixed reality headset who wants to explore the dynamic abstraction in physical space. Or you might consider someone walking home and who wants to listen to this new development in physics and try to understand the benefits of this abstraction and these kind of interactions. And finally, you might find people who apply these new interactions and this dynamic abstraction to new domains in much the same way that we might take apart the pieces of a car and apply them to build something new. What this really underscores for me, that I keep going back to in a lot of my work, is that the chief power of a lot of these large language models today is really performing what I call translation work, or translating between representations. And in the past, it was really hard to get computers to do this in a way that approximated human behavior. And when this translation work is done on behalf of the user with their unique context and grounded in, for instance, in this situation, in their physical world, we call it dynamic grounding. And this is a concept where we develop AI systems which meet us where we are on our terms. I'm just going to give you one more example to try to underscore what I mean by dynamic grounding. So imagine we have a very simple notational system where we just have an X and an O. And we say with the X, this is a cat, and with the O, this is a mouse. Even with such a simple system, we can imagine AI systems where we can ask questions like, what's happening here? Or we could instruct the AI system to say, the mouse's friends arrived to rescue them. And then the AI system needs to add the X's in the appropriate place and understand what we mean. One example of this in recent work that I really love by Ryo Suzuki and Rubiet and others is Reality Sketch. In Reality Sketch, you can draw these abstract representations on top of physical objects. And then you can move the physical objects and it will move the abstract representation. And so this is really a great demonstration of grounding at work, where the abstract representation is grounded and projected onto a physical object in physical space. And you can then explore the system that this dynamic abstraction has created interactively using your hands. It's quite interesting work. And this is just one example. There's many other people who are working both on the grounding problem and on making these systems more social. For instance, Dynamic Land by Brett Victor, WebStraits, the Dynamic Documents projects of Ink and Switch's research lab, and many other researchers in HCI.
All right, so looks like we're almost at the end of our trip. So Feynman has shown us how he developed his diagrams in this parallel universe, which was fascinating. He went through the process of abstraction, which is, quite similar to our universe, but in a dynamic media. And then not only that, he created a dynamic simulation based on this abstraction by assigning rules and behaviors. And then finally, he created ladders of abstraction, as as Sang-ho and Sakib covered. And as Ian mentioned, it was spread and shared through the process of dynamic grounding using a dynamic shareable media through the internet. So let's thank Richard Feynman. We have learned a lot, and I hope each of us have taken something from this experience. So thank you so much, Dr. Richard Feynman. We hope to see you again in the future. All right, so I think it's time to get back to our home. Guys, any thoughts?
Well, I can go first.
Yeah.
Well, I mean, that was very inspiring, of course. Like the parallel world we're talking about hopefully is going to happen in our world, hopefully very soon with the help of AI assistants. And some of the work that I have shown in mathematics, I think AI generally will have a lot to contribute in solving these difficult inverse problems when we are moving between different abstraction layers. So I am excited about new AI methods and technologies that can allow me to do that. And I'm looking forward to a world where we do math primarily in visual and embodied mediums.
Yeah, I'm really excited about how it would enable creators to create their own tools, in contrary to what many creators believe that how AI threatens their creativity. But I believe that it will give them more agency because they can tailor the tools, create their own tools. And I think it's not just the use of technology, it's also like a specific way of thinking, as Brett Victor mentioned at some point, that ladders of abstraction is a powerful way of thinking. So I hope more and more creators will think in this way with dynamic abstraction. I think it's a very powerful way of thinking.
Yeah, and for me, I think I love how we came from different from different angles and contribute different parts that can help us like move forward in this field, right? And like so as Rubai mentioned, right, we have you know founded this community to invite people who are interested in this vision to come in and contribute insights and ideas. And I think what I really look forward to is just like really learning from how all these different research existing work can help us move forward, because like dynamic grounding that Ian mentioned, these layers of abstraction work that Sakib did, Rubaiyat's work that with animation, and all these work are I think building blocks, abstractions that can help us achieve what we envision as dynamic abstraction. So yeah, I think one takeaway for me is the importance of building a community of people who have the same kind of inspiration to make the future possible, right? And so I hope people who also join in to listen, to kind of chime in and contribute their insights so that we can also learn from each other and kind of collectively move forward together. Yeah.
I think Sang-ho, you said that very well. I will just add that I think there's a lot to do in this space. That even seemingly simple things like the cat and mouse example that I gave are actually quite hard to pull off with current AI models. And I think there's a lot of room to grow. I personally look forward to practical work with real people, working on specific problems and imagining what dynamic abstractions looks like for them in their particular circumstance. And then taking insights from that and applying it to other domains. So I think a lot of this work could probably proceed not abstractly, but originally through concrete work and arising abstractions through that concrete practical work in the exact same way that, as Sakib and Sang-ho mentioned, abstractions arise by necessity through encountering these concrete problems.
Fantastic. Last of all, thank you so much for all of your work. It's been a while. We have been working on this space, and I'm really glad we did it. And thanks to all these contributors listed in this screen who have contributed through ideas and conversations and some of the projects we have shown today. So if you're really interested in this space, feel free to join the Discord channel. Thank you so much.